Chapter 15 here, which is about solutions. So we're going to talk about different properties of solutions. We're also going to talk about concentration with solutions, and we will also talk about stoichiometry that involves solutions. So let us start with just solutions in general. So a reminder, we talked about a couple of times, obviously, throughout the semester, but many important biological reactions and a lot of other sort of chemical reactions do occur in an aqueous environment, and aqueous is really those guys that get the AQ symbol next to it. And it really means a solution, and a solution is a homogeneous mixture of two or more substances that are together. Homogeneous means that it looks the same throughout, so everything mixes, right? That's different, obviously, than a heterogeneous mixture that we talked about earlier on, where things really do not mix and you see different layers. So a solution is always homogeneous, and there's really two parts to a solution. There is what is referred to as the solute, and that is the smaller part of the solution. And there is the larger part of the solution, which is the solvent. So both of those things together make up what a solution is. So both of these guys are needed for a solution. So for example, if we made a solution by taking water and some sodium chloride here and putting them together, we would get a sodium chloride solution that would get an aqueous solution. The salt would dissolve obviously in the water. In this particular example, it is the solute here, which is the smaller part that's dissolved. And in this case, it is water, which is the solvent in this case. Water is a very common solvent, as we'll talk about. It works well for a lot of things, especially ionic things, polar things, but it's not always going to be the best solvent in some situations. But in a lot of ionic situations and aqueous type situations, a lot of times water is the solvent. How do you know what the solute is in a solution? It's pretty simple. It is the name of the solution. So if you have a sodium chloride solution, sodium chloride is the solute. If you have a calcium chloride solution, calcium chloride would be the solute. So pretty much the name of the solution is always the solute. And again, if it's ionic, it's probably going to be water as the solvent. But again, it may not always be water in a lot of cases. So water, which is a very effective solvent for a couple of reasons, obviously is pretty non-toxic, but really water works really well because it is a polar molecule where oxygen is more negative. The hydrogen side of water is more positive. So it's able to interact really well with a lot of substances. It's able to interact well with other polar molecules using dipole interaction that we talked about the other day. It also could work really well with a lot of ionic compounds using that ion dipole sort of interaction. So when we get something like sodium chloride we were just talking about, basically what's going to happen is the negative side again of water is going to surround it, help really that sodium chloride sort of dissolve in solution. And when we have like our negatively charged ion, it is the positive side of water, which is the hydrogen, that will basically surround it and also help it to basically dissolve. So this is really those intermolecular attraction or forces that we were talking about in the previous chapter. And this is sometimes referred to as ion dipole interaction. Ion because of sodium chloride or ions, and dipole because water is a polar molecule that has a dipole moment. So that helps them dissolve and interact really well in that process. We're able to help that out a lot, right? When we go to dissolve something, because we start to stir it, right? Adds energy, also throws a ton of waters all over the solid, and it helps in that sort of dissolving process. So that process there is sometimes referred to as hydration. It is what allows those ions, which are extremely attracted to one another, to really dissolve and stay apart. Just the amount of water that's present is enough to sort of rip apart those ions from one another. We also know that, again, this is a physical change, right? When we make a solution, because it is a homogeneous mixture, It is a physical change. There is no chemical change that's occurring. We know that both things are still there because, again, as we've done a number of times, if we were to heat this solution, evaporate off the water, these two ions would then come back together and we would re-see that solid that was there originally. So remember, a solution, which is a homogeneous mixture, is also just a physical sort of change that's occurring. We just can't visually see the sodium chloride anymore because there's just so much water molecule surrounding each of the ions that is no longer sort of visible to us to look at. Here's a picture of that. Again, this is what an ionic solid looks like. It's a really organized array of ions together. As we talked about a little bit at the end of that last chapter, it's sort of minimizing the repulsion forces, sort of maximizing the attractive forces. But basically, water molecules come through and they basically just kind of pick off some of that solid. And once again, we do help this process along by stirring. That again throws a lot of water molecules over that solid and again provides a lot of energy needed to kind of get that whole process going. So when we talk about bonding, it's important here, again, a reminder when we talk about the different types of bonds that we have before, ionic bond always between a metal and a non-metal. And again, that is the opposites attract or electrostatic attraction that occurs. Remember, that's different than what we have with covalent bonds, where we do have sharing of electrons. Depending on sort of the bonding, and especially with covalent, we may end up with sort of a polar molecule, which may work really well in certain situations and be soluble with other polar molecules, or we may end up with a non-polar molecule depending on obviously the electronegativity difference between them. And that's just some stuff that we talked about, obviously, about polar bonds and covalent bonds. So these things really do help us understand the solubility of things in, for example, water. So, for example, water, which is polar, it's going to be really, things that are ionic are going to be really soluble in it because, again, we're going to get that ion-dipole interaction that's going to occur. So pretty much anything that is ionic, water is a really good sort of solvent for it. Again, doing that ion dipole sort of attractive force that's happening between them. But there are some non-ionic compounds, which are also very soluble in water. Things like sugar, things like ethanol are also soluble in water. And if we look at something like ethanol, which looks something like this. Ethanol, which is really an organic sort of compound, really kind of has two parts to it. There's sort of a part of this molecule that if we look at is pretty much non-polar, which is pretty much this part of it. This is all like non-polar. That is all carbon and carbon bonds, and that is carbon-hydrogen bonds. But what allows something like ethanol to be soluble in water is it actually does contain a polar part, which is this bond right here. And that bond is a polar part between oxygen and hydrogen. Again, the oxygen being more negative in that bond, hydrogen being more positive. So because it has this polar part, it's able to interact really well with water because water is pretty much identical. It has that negative and positive. So when these two guys get together, the positive side of one is attracted to the negative side of another. That is a bond between hydrogen and oxygen, which means this is an intermolecular force known as hydrogen bonding, like we talked about in the last chapter. So it's able to hydrogen bond with water, which makes it really soluble in water. So even though it is not ionic, it has that polar part and it's able to interact. So in terms of solubility, as we'll be seeing sort of in this chapter, what's really important for things to be soluble in each other is they're able to use the same sort of intermolecular force that they use with themselves, and they could use it with somebody else that uses the same type of intermolecular force. So if we get two things that really are using the same sort of intermolecular force, they tend to be really soluble in each other. Sugar, which is a little larger of a molecule, contains carbons, hydrogens, and oxygen, but as we'll see a picture of it in a second, sugar is pretty much loaded with OH bonds all over it. So everywhere there's an OH bond, it allows something like sugar to interact well with water and hydrogen bond, and it makes something like sugar very soluble in it. We will talk a little bit about it, but solubility will decrease. So for example, if you take other organic molecules that have a lot more carbons and hydrogens attached to the sort of the non-polar side, the solubility drops down to like nothing at that point. It just becomes too large for it to interact with it. Yeah.
How will it stay together?
It would, because it's covalently bonded, so everybody's sharing electrons. So it will not break apart when it goes for a swim. It basically will all stay together as a whole molecule. But having that OH bond there is what allows it to interact with water. But yeah, it definitely will not break apart. Other questions? So as I was saying, as you sort of increase the carbon and hydrogen, is really the non-polar part of something like that. There's an organic molecule like this, solubility really starts to drop. So right around 5 or more carbons, you see the solubility pretty much drop, because again, what happens in that case, if you build out sort of this non-polar side of it and this part becomes much longer, it just gets too big for that OH group to really make a difference. It's sometimes referred to as steric hindrance. The kind of big part gets in the way of the OH being able to interact with everybody else. So the solubility really starts to decrease. But sort of molecular compounds or organic sort of compounds like this that have smaller number of carbons but still have that OH part are fairly soluble in water. This is another example. This is methanol here, or methyl alcohol is sometimes referred to. And again, it has that OH group there, which is polar, going to allow it to nicely work and hydrogen bond with water, and makes methanol very soluble in it as well. Here's our ethanol picture again. So what about oil and water? Do they mix? And as you might know, oil and water do not mix. Pretty much oil is nothing more than long chains of carbons and hydrogens together. So they're really just long runs of just carbons attached to carbons, and attached to those carbons, hydrogens. And because of that, it's a pretty big non-polar molecule. And as we were talking about in the previous chapter, when non-polar molecules sort of use intermolecular forces, they use those dispersion forces. So if you remember, those intermolecular forces for non-polar molecules are dispersion forces, which are relatively weak and not very strong type of intermolecular force. And when this guy, which wants to use dispersion forces, comes along with water, which really wants to use hydrogen bonding, we get sort of a conflict that happens. They basically are not trying to use the same type of interaction with each other, and they have no long way to maintain that interaction. So as we talked about maybe a little bit last time, you could put some oil and water right together, and maybe it'll mix for a bit, but eventually over a long period of time, they'll kind of separate out from each other. And that's because both of them, water and oil, can use dispersion forces, but because that dispersion forces are really weak force, it's not going to be able to maintain that interaction for any long period of time, and they really will sort of separate out from one each other. So oil is insoluble in water because of that. And it really brings up an idea about sort of solubility. So for example, in order for something like say oil to mix with water, before we put anything into water, water is basically hydrogen bonded to a bunch of other water molecules, right? So they're all hydrogen bonded to each other. So in order to fit something to dissolve in water, we have to break apart the water-water interactions and basically try to replace them with something that's very similar. So in this case, if we try to replace it with something like oil, it's big, it's basically has no way to interact well with water. It's just not going to fit very well with water. And again, that's why they really aren't dissolving each other. You know, kind of like, again, if you took like a big truck and you parked it into a garage, you could maybe get some of it in there, but it's really not going to fit really well if you had like a semi truck or something and try to pull it into a garage. And, you know, maybe it'll work for a little bit, but you can't get it all to work. And that's the same idea here. So when we talk about solubility of things, it really boils down to the idea of what is referred to as like dissolves like. And like dissolves like means that things that have similar intermolecular forces with how they work with themselves will be soluble in other things that are using the same intermolecular forces. So really what that boils down to is things that are soluble in each other are things that are ionic and polar because they could do that ion dipole interaction. Things that are polar and polar can work well with each other because it could do dipole-dipole or hydrogen bonding. Things that sometimes people miss as well is nonpolar things, and nonpolar things will also be soluble in each other. So they both are going to be using dispersion forces, so they're able to interact well with each other because frankly, they're both using the same type of intermolecular force. You really kind of only run into some issues when you kind of cross over. So when you kind of go polar and nonpolar, not so good. That is going to be typically insoluble in each other. So that's sort of a really quick way to make a prediction about solubility is, you know, okay, this guy polar and this guy's polar, they probably should mix. If this guy's polar and this one's non-polar, they probably won't mix. So it's a really sort of easy way to figure out, you know, should these things be soluble in each other? Any questions on that there? So here's a picture of sugar. And again, as you can see, although it's a little bit larger of a molecule, it is pretty much littered with OH groups all over. So everywhere there's an OH group on that molecule is a place where water can interact well with it. And again, that makes sugar relatively pretty soluble in water. Again, down here is our oil, which is just a long chain of carbons and hydrogens, right? When we go fill up our gas for, you know, octane, which is like 8 carbons together, they break that apart, and you get your different things like gas and stuff like that from these long molecules. This is typically what we see. Again, typically the nonpolar layer there's up on top, the water layer is usually on the bottom, and again, there's usually that separation. In the water, again, we got all that hydrogen bonding happening with the water molecules and water molecules. And again, that oil has really no way to interact well with it. So solubility, when we talk about things being soluble, when one substance is soluble in another or dissolves in another, I guess that's the way you can say that. If one substance, a solute, dissolves in a solvent, it is said to be soluble. Salt is soluble in water. When one substance does not dissolve in another, it is said to be insoluble. So oil is insoluble in water. Sometimes when we talk about liquids, we use the words miscible and immiscible. And miscible means that it all dissolves. Basically, all looks like one layer. Immiscible means that we would see sort of different layers. So sometimes instead of soluble and insoluble with liquids and liquid sort of interaction, miscible and immiscible are sometimes used, and they mean kind of the same idea there. Miscible basically means soluble, immiscible means insoluble. There are usually a limit to the solubility of one substances. Gases are always soluble in each other, and the reason gases are always soluble in each other is they are flying around, which means they are constantly mixing as they are flying around, which means they are soluble in each other. Some liquids are also always miscible in one another and are soluble in one another, and that is things that are polar and polar, non-polar guys together will always be soluble in one another. So that idea of like dissolves like is really important, and that's why earlier when I mentioned water is usually a very common solvent, but it's not always the best solvent. So if you try to use water as a solvent for a non-polar compound, it's not going to work because again, they're going to be trying to use different types of interactions. So in a non-polar guy that you want to dissolve, you need to use something that's non-polar as well, and that usually will help. So when we talk about the solubility of a solute, it does depend on temperature. So at a higher temperature, we have a larger solubility of solid in a liquid. So as you increase the temperature, that allows more energy. And as you allow more energy, that usually will allow more solid to dissolve than at another temperature. So solubility is based on temperature. And again, usually increasing the temperature will increase the solubility of a solid in a liquid, and vice versa. If you kind of decrease the temperature, usually we'll see a decrease in the solubility of a solid in a liquid. At a lower temperature, we have a larger solubility of a gas in a liquid. And if we think about a lower temperature in terms of gases, my gas molecule would be moving a lot slower at a lower temperature, which means if it's in the liquid part, it's going to be in there for a much longer period of time at a lower temperature, rather than a higher temperature where it has more energy and be able to basically escape out of the liquid part a lot quicker. The solubility of a gas also depends on pressure. The higher the pressure, you have the larger solubility of a gas. And that's because at a larger pressure, you have a much smaller volume, right? So the gas is in a much smaller volume. It's like the soda can sort of idea that's sometimes referred to as Henry's Law, right? In a soda can, before you pop the lid, there's a lot more of the CO2 basically dissolved in the liquid part, which keeps your soda fresh. You pop the top, you release the pressure, right? And sometimes you see the fizzing that comes out the top, right? That fizzing is the CO2 escaping. And that's why when you leave your soda thing can open for a while, you come back to it, it tastes a lot flatter, right? Because you gave your CO2 place to escape. It escaped, it got blown away by the air, and now your soda tastes flat in that situation. But before you pop it, there's a lot more of that CO2 because it's going to be a smaller volume dissolved in the liquid part of it as well. When we talk about composition of solutions, there's a couple different ways that we classify solutions. One is what is referred to as a saturated solution. And in a saturated solution, that is one where you pretty much have hit the maximum amount of solute that will dissolve at a given temperature. So it is the point where pretty much if you add more solid to it, it will not dissolve anymore, pretty much. There's no more that will dissolve. It will just start piling up on the bottom. The opposite of that is an unsaturated solution. And in an unsaturated solution, you pretty much have not hit that point yet. So if you take more solid and you want to dissolve it, it will continue to dissolve until you hit what's known as the saturation point. And that is the saturated solution at that point, and then it will stop dissolving. So like if you took some water and you took some sugar and you put it in there, it should dissolve. But if you continuously take like the Costco size sugar, right, and you dump it all into that cup of water, at some point, it's obviously not going to dissolve. You've hit a saturated solution and you'll have stuff basically just piling up. But before that, it will continue to dissolve until you basically hit that saturated solution. Another way that you can classify a solution is what is referred to as a supersaturated solution. And in a supersaturated solution, you have too much solute dissolved at a given temperature. And what that creates is really almost like an unstable solution. So how you typically make a supersaturated solution is you pretty much will like heat up some, say, water. And as you're heating up water, you're going to dissolve a bunch of solute in it. And what that does is two things. As you heat up the water, it allows a lot more of the solid to dissolve, right? Because it's at a higher temperature. You're also evaporating off a little bit of the solvent, the water at that point. Then typically when you get a lot of it dissolved, what you do is you take that solution and you pretty much leave it alone, let it kind of cool back down. So as you let it cool back down, what happens to the solubility is the solubility starts to drop, right? Because now it's at a cooler temperature. Problem is, at this point, you've already dissolved way too much solid for this lower temperature. So you have a solution that's now at a lower temperature, has way too much stuff dissolved in it, and that's why it's really unstable. It's so unstable that, frankly, you could take just a barely seen crystal of whatever you dissolved in there, and if you drop it into the solution, which is basically liquid at this point, sort of an aqueous solution, it will cause this solution to go, whoa, too much solid here and there. And all the solid will start to come out of solution, and it will go from a basically liquid state into a solid state. It will force all that solute that you dissolve basically to come out of solution. It's actually sometimes so unstable, we might see it later today, that if you just accidentally like knock the flask there or whatever, it will cause it to just come out of solution without even adding anything to it. So sometimes you could just like bang it. I've done it before in that demonstration, like just taking it out and put it down, it just comes out of solution that quickly and stuff like that. So a supersaturated solution is one where you have way too much solute dissolved at a given temperature in it. And again, it creates this sort of unstable solution. And we'll see it in lab in just a bit here, an example of that. Any questions on that? All right, some other ways that we could classify or describe solutions. Concentrated. Concentrated is a solution that contains a relatively large amount of solute dissolved in it. Perhaps you've seen the very common unit of concentration on bottles, which is molarity. And that's what the big M stands for. And the higher the number next to it, the more concentrated it is. And what we usually use, though, obviously in labs and a lot of experiments, is a more dilute solution. In a more dilute solution, we have less solute dissolved in it. And typically how we go from a concentrated solution, which is sometimes referred to as a stock solution, to a dilute solution is we do a dilution, which means we basically, in a lot of cases, just add more solvent like water. So as we add more water, it actually dilutes down the solute that's in that solution. Going back to a common example of that is, again, you get like the big gulp there before class, right? With all the ice in it. Tastes good, you drink it, you come back, leave it in your car. After class, you come back, all the ice is melted, right? Your soda does not taste as good as it did before because it's now been very much diluted, but you still drink it thinking, how bad could it be, right? Then maybe you regret that decision later. I don't know. We'll see. We've all done it. There's no shame. All right. Let us talk, though, about concentrations of solutions. So the first type of concentration that we're going to talk about in terms of a solution is what's referred to as mass percent. This is sometimes referred to as percent M/M, which is mass to mass percent. And to calculate the mass to mass percent, it is the mass of the solute divided by the mass of the solution times 100%. And when we do these type of problems, it's really important, actually, the bottom part here, which is the mass of the solution. That is, again, the two parts, which is the mass of the solute and the mass of the solvent. And you want to make sure that when you do these calculations that you really do get both of those together. And the reason why you might not get both of them together is it's very common in these type of problems. They give you those numbers separate from each other. So they'll give you the mass of the solute, they'll give you the mass of the solvent. And it's a very common mistake that people make, which is they just divide by the mass of the solvent because they go, oh, that's a larger number, I'm just going to divide by that. So you got to make sure a lot of times in this situation that you actually do add them together. This is basically grams divided by grams in most cases, times it by 100 to get it into a percentage. So let's take a look at this one here, or one of these. What is a solution is prepared by mixing 2.5 grams of calcium chloride with 50 grams of water. Calculate the mass percent of it. So take a moment and calculate that, see what you come up with. Okay, let's take a look at it. So first in this case, we're going to try to find the percent mass to mass, which is, again, the mass of the solute divided by the mass of the solution times 100%. So in this particular case, it is the calcium chloride here, which is our solute, as it is the smaller part here. It is the water here that is our solvent. So our mass of our solute in this case is going to be 2.5 grams. The mass of our solvent in this case will be 50 grams. So we do have the mass of the solute given to us. So once again, here we do not want to divide by 50 as that's just the solvent. So to get the mass of the solution, we do need to add both of those things together. So that's going to give us 52.5 grams as the mass of the solution. Now that we actually have the correct mass of the solution here, we can put it in. That's going to give us 2.5 grams divided by 52.5 grams times 100%. Again, the grams will cancel here. Leaves us with a percentage. And if we do that, looks like 4.76. The way you could kind of give units here is percent. Usually do parentheses mass to mass in there. And then if you want, you could put calcium chloride at the end there. That's there. Any questions on that there? All right, let's take a look at another one then and see. All right, concentrated hydrochloric acid solution contains 37.2% by mass HCl. What is the mass of HCl contained in 35.5 grams of the concentrated hydrochloric acid solution? Just to let you know. Mass to mass, which is our mass of solute, our mass of our solution, times 100%. In this case, we are given the percent mass to mass, which is 37.2%. We also are given the mass of the solution, which is 35.5 grams. And we're looking really for the mass of the solute, which is basically the grams of HCl. How do I know we are looking for the mass of the solute? If I didn't write solution on that, again, the name of the solution is the solute. So if you're looking for the grams of HCl, you're clearly looking for the grams of the solute in this particular case. So there are a couple of ways you could solve this. One way is you could obviously just plug and chug into the equation there as well. You also can, if you wanted to, use the percent mass to mass as like a conversion factor and sort of do the calculation dimensional analysis way. So when I have something that is 37.2% by mass, what that basically means is I have 37.2 grams of HCl in 100 grams of solution. So that's basically what the 37.2% means. We could use this like a conversion factor. We could use it like that. We could also flip it around and use it the other way, where we put the 100 grams of solution up on top and the 37.2 grams of HCl on the bottom. So if you took more of a dimensional analysis approach to this problem, we could take our 35.5 grams of solution. We'll use the correct conversion factor that we're looking for, which would be this one. And we could take 37.2 grams of HCl over 100 grams of solution. The grams of solution will cancel. That gets us basically here 35.5 times 37.2 divided by 100 gets us 13.2 grams of HCl. Question on that there. So if you do have some type of percent concentration, you can turn it into a conversion factor by just assuming 100 grams of solution. And sometimes it's easier. Obviously, if you went into our equation, it is the exact same calculation. Basically, you would do this. You would do your mass of your solute. You would do your 35.5 grams, and you do 100%. You would divide this to the other side, and you would then multiply that guy. And that's basically the exact same thing that we just did over here. And you should end up with the same answer. So again, you could plug it in there, or you could take more of a dimensional analysis approach. Question on percent mass to mass. Now, in addition to percent mass to mass, there are a couple of other sort of percent concentrations that sometimes are used for solutions. So let's just talk a little bit about those before we go on to really the main one that we talk about most of the time. I'm just going to steal, I think, some of this here. So a couple of other sort of percent concentrations in addition to percent by mass is there is percent by volume, which is percent volume to volume. And that is the volume of solute divided by the volume of solution. times 100%. That's like, percent by volume alcohol type of deal. Yeah. So that's basically what percent volume is. That's usually milliliters over milliliters. And again, those units will typically cancel out and you'll be left with a percentage. The other common one is percent mass to volume, which is the mass of the solute divided by the volume of solution times 100%. That's basically grams over milliliters. It's basically density. If you multiply it by 100, it's basically kind of the same idea as there. So percent mass to mass, percent volume to volume, and percent mass to volume are three common percent concentrations that are used. Really only the mass to mass is the one you gotta have to worry about, that bottom number there with the mass of the solution. The other ones where you have the volume of solution is usually given to you, so you don't have to worry too much about that. But for any of those, you could turn them into a conversion factor. So we just saw what we could do with our 37.2% mass to mass. If we had 37.2% volume to volume, whatever this was, calcium chloride, that would mean we would have 37.2 milliliters of calcium chloride in 100 milliliters of solution. Or again, we could flip it around. 100 milliliters of solution would be our 37.2 grams of calcium chloride. And if we have 37.2% mass to volume calcium chloride, it would work the same way. That would mean we have 37.2 grams of calcium chloride in 100 milliliters of solution. Or in 100 milliliters of solution, there would be 37.2 grams of calcium chloride. So for any of those sort of percent concentrations, if you're given the percent concentration, you can turn it into a conversion factor and just sort of do a dimensional analysis sort of calculation. Any questions on any of those there? Okay, so the next that we're going to talk about then is really probably the most commonly used unit of concentration of them all, which is molarity. And I would say pretty much that's usually what you're calculating, and that's usually what solutions are given to you in, is actually molarity rather than any sort of percent concentrations. So let's take a look at that. So molarity, which is, again, like I said, the most common unit of concentration, is abbreviated with a capital M. And when you see the capital M, it really stands for the moles of solute divided by liters of solution. It's basically the real sort of definition of it. You could think of it like a formula, kind of like density. We oftentimes use molarity and we solve for any of those three things. We sometimes solve for molarity, we sometimes solve for moles, and we sometimes solve for liters. So if you have molarity, again, it is moles divided by liters. If you want liters, which is a common calculation, that is moles divided by the molarity. And if you want moles, which is an extremely common calculation, you take liters times molarity. So those are sort of three versions of sort of like the molarity equation. It is sort of like an equation, and you do need to be able to rearrange those. We will solve for all three of those things at some point in this semester, in this chapter as well. Molarity is moles per liter. And it's really important that if you use molarity, that you do use it with liters. The other really important thing is, frankly, if you are given the molarity of something, you get rid of the big M and you put both units there, because it is a very common mistake that people make, that they do not get rid of the big M in calculations and they forget all about the liters part. Like there's a volume there, I'm not really sure, and they just think in their head moles a lot of times when they see the big M. So if you had something like a 4.50 molar solution of sodium chloride, what that basically is 4.50 moles of sodium chloride per liter. So the number always stays with the moles part, and it's always per 1 liter. And when you're doing calculations, that's probably the best way to do it, is convert it into both units, so you can see it as both units being there, so you don't forget about the liters part. You could also use this really as a conversion factor as well, and to do dimensional analysis. If you needed to, you could flip it around and use it the other way. So if you wanted to use it more like a conversion factor, again, we could go liters on top and 4.50 moles in this example is sodium chloride on the bottom. So again, highly recommend don't leave the big M in the calculations, convert it into moles per liter so you can see both units, and hopefully you won't forget about either of those units, which is a very common error. So when we have something that is 1.0 molar, that's how we refer to it. It is written in terms of before it dissolves. So 1 molar sodium chloride would contain basically 1 mole of sodium chloride dissolved in enough water to make 1 liter of solution. It also would contain 1 mole of sodium ions and have 1 molar sodium and 1 molar chloride. So how ions work in concentration in terms of molarity is if we have sodium chloride, because it's a strong electrolyte, when it's in solution, it really is a sodium ion and chloride ions floating around. And if the whole thing here was 1 molar, we could kind of do a stoichiometry relationship between the whole thing and each of the ions. And it basically is a 1-to-1 relationship between these two, which means if we were interested in just the sodium ions, it would be 1 times 1 molar, which would give us 1 molar still. It is also a 1-to-1 relationship between the whole thing and the chloride ions, which means we would take 1 times the 1 molar, and that would give us 1 molar for the chloride ions that are floating around in there. So sometimes you are asked about maybe not the whole ionic compound, but you're maybe asked about the concentration of one of the ions floating around in the solution, and you can relate it to each other like stoichiometry. So for example, if we had calcium chloride here, that was 1 molar. When calcium chloride breaks apart in solution, you get a calcium ion and you get 2 chloride ions in this case, right? Now, when we think about the concentration of each of the ions that are floating around in there, for every 1 calcium chloride, you get 1 calcium ion, which means the concentration of the calcium ions in that solution is 1 molar. When you look at the chloride ions, for every 1 of the whole thing, we actually get 2 of the chloride ions, which means you actually need to multiply the concentration by 2. And the concentration of chloride ions in that solution would actually be 2 molar. They are not additive. Clearly, 2 and 1 does not equal 1, right? But that's basically the proportion of ions that you get per molecule. So if you just logically think about it, you basically get a 2-for-1 deal here, right? So you get 2 chlorides for every 1 calcium, which means you have twice as much chlorides in that solution. It's twice as concentrated in terms of chloride as it is the calcium. That is the short version of that calculation. The long version of that calculation is this. It is actually like a stoichiometry calculation. You take 1 moles of calcium chloride per liter. You do a mole to mole relationship between these two, which is 1 mole of the whole thing gives us 2 moles of the chloride. Moles of the whole thing cancels out, leaves us 2 moles per liter of chloride, which is why we're multiplying by 2. So that's kind of the quick way of doing the calculation. If we did it for the calcium, we would have 1 mole of the whole thing over a liter, which is the molarity. It is a 1 mole of calcium chloride to 1 mole of calcium ions from the equation here. These guys cancel, leaves us basically 1 mole per liter of calcium. So that's really the long version of if it breaks apart into a 1-to-1, just multiply it by 1. If it breaks apart into a 1-to-2, multiply by 2. If it breaks apart into a 1-to-3, multiply the concentration by 3. So that's how you can relate the concentration of the whole ionic compound to the concentration of each of the ions. Any questions on that there? And again, sometimes you will need to do that as you're interested in maybe just one of those things. A standard solution is a solution whose concentration is accurately known. You will be making one, I think, in lab today, a standard solution. Basically, you use the molarity to figure out how many grams you might need to make that solution. All right, so let's try one here. Calculate the molarity of a solution that's prepared by dissolving 15.6 grams of solid potassium bromide in enough water to make 1.25 liters of solution. Potassium is, I think, 3910, and bromide is 7990, I think, for the periodic table. All right, see what you come up with here. Calculate the molarity of this solution. Okay, let's take a look. So clearly we're looking for the molarity, which is our moles per liter. We have the grams of KBr, and we do have the liters of solution. So we actually do have the bottom part. We do need to get to the moles part, but we could do that because we do have the grams of our solute here, which is the KBr. To get to the moles, we obviously need to use the molar mass like we've done before from the periodic table. So in this case, we're just going to actually add these two numbers, I think. It's going to give us a $1.19, I think, here. So we're going to convert our grams into moles. So we'll take our 15.6 of KBr grams. We'll divide it by the molar mass here to convert it into moles from the periodic table. And that's going to give us 15.6 divided by 119. We're going to go with 0.131 moles, which is really the top part of what we need. So now that we have the top and the bottom here, we can calculate the molarity. That will give us 0.131 moles over 1.25 liters. It gives us, we'll call it 0.105. Now the units here really don't cancel, so you can leave it as moles over liters. So again, the number always with the moles in is 1 liter, and you can put KBr. Or you can at this point, if you want, convert it back into big M and write it like that. So either way would be sufficient. Any questions on that one there? All right, let's take a look at another one here. Actually, we're going to skip a couple of examples. We'll come back to them next time, but I think we'll do this next one first, I think, wherever it went. Let's do that one. All right. So let's try this one here. What is the mass in grams of a sodium nitrate solution that's required to make 2.5 liters of it, and make sure that it's 0.15 molar? So give it a go. Sodium is 2299 grams per mole. Nitrogen is 1401 grams per mole. And oxygen is 16. All right, so we're looking for how many grams I need to weigh out to make this solution. So see what you come up with here. All right, let's take a look. So in this case, we really want to figure out how many grams to make the solution. So we could use our molarity equation, obviously, to help us. In this case, we are given, obviously, the liters here of 2.5 liters. So we do have that guy. We're also given the molarity of 0.150 molar, which means we have this guy. We could rearrange this, obviously, and solve for moles, which will be liters times molarity. You always want to make sure that it is in liters, the volume, when you are dealing with molarity, and not milliliters. So milliliters is a common unit that you have volume in. So very commonly, you do need to convert milliliters to liters when you're dealing with molarity. So a reminder, right, that's 1,000 milliliters is a liter. So that's a very common conversion that we use a lot with molarity. We also, as we talked about, really do want to sort of get rid of the big M and maybe take a more dimensional analysis approach to this calculation. So here, what that would mean is we have 0.150 moles per liter of our sodium nitrate. Once again, that allows us to see both of the units so we don't forget about it. So in this case, we would take our liters, and as you do it like dimensional analysis here, You can see why it does need to be in liters so that the units do properly cancel out. So those liters will cancel. This will give us 2.5 times 0.150, gets us about 0.375 moles of sodium nitrate, right? Any questions on that so far? So now that we have the moles of our sodium nitrate, which is our solute, it's really how much we want to weigh out. We need to convert it into a usable unit, right? And we got to go from moles to grams, which is again another very common conversion used with molarity, and that's going to be the molar mass like we used on the previous problem to do that. So in this case, we do need the molar mass of sodium nitrate. And if we add it up, that's 2299 grams per mole plus 1401 for our nitrogen plus 3 times 16 for our oxygens. That's going to give us, I think, 85 grams per mole. So we'll use the molar mass there from the periodic table to do our conversion here so that we know really how much to weigh out. That's going to be 85 grams on top, moles on the bottom so that they cancel. If we do that, we end up with about 31.9 grams of sodium nitrate is needed to be weighed out. So if you were to make this solution, you would weigh out 31.9 grams of sodium nitrate. You would dump it in enough water to dissolve it and take that water volume to a total of 2.5 liters. After you would mix it together, you would then have a solution that has a molarity of 0.15 in this case. Yeah. So again, you would put the solid in, put the water in, mix it up to the 2.5 liters. And again, you would then have that proper molarity of solution. Question on that there. So just to finish on here for today, what happens if we do take in our tendency to maybe not convert things? If we do take milliliters times molarity, do we get something? What we actually get is what is known as millimoles. Not moles, it's millimoles, like 1,000 of them. So if you take milliliters times molarity, you're going to be off by a factor of 1,000 because what you're really calculating is what's known as millimoles, because molarity can be thought of as millimoles over milliliters, which means when you cancel out the milli on top and the milli on the bottom, you're back to moles per liter, which is molarity. So you do get something when you multiply molarity by milliliters, but it's not moles, which is probably what you're probably thinking it is. It is millimoles, which means, again, you're off by that factor of 1,000. So you got to be safe. You should probably always, in most cases, especially if you're using molarity by itself and volume by itself together, always convert it to liters. So you'll be in the right units that you need. Any questions on that there? All right, we'll lay it up there for today.